This presentation will review condensers. The condenser rejects heat absorbed by the evaporator. Three phases of a condenser. What happens inside the condenser is the refrigerant must first be de-superheated because of the high temperature vapor that's coming out of the compressor because of the compression process. So we need to de-superheat, which is going to reduce the discharge temperature so that the second phase can occur, and that is to condense, going from a vapor to a liquid. Latent heat is removed, so we're going to go through that phase change from vapor to liquid, and then the last few passes of the coil, condenser coil, will reduce the temperature below the pressure temperature relationship, the saturated condition, and that will be sensible cooling, known as subcooling. Here we have a typical air conditioning condenser, a walk-in actually, in this case a walk-in refrigerator. We're looking at the box temperature of 35 degrees with an outdoor ambient of 95 degrees. We have a 50-pound back pressure and a 280-pound head pressure. And we're coming out of that compressor very, very hot at 175 degrees, so it is superheated. It is above the pressure temperature saturation condition. Now, the PT relationship for saturation is 280 psig of R22 would be 125 degrees. So from 175 degrees to 125 degrees, the condenser has de-superheated. So the condensing can start, and at some point in the coil, the entire vapor will be condensed to 100% liquid. When it gets to 100% liquid at 125 degrees, you'll notice that we have 95 degree air passing over the condenser. That means that heat goes to cool, high temperature goes to low temperature, so 125 degrees is hotter than 95 degrees, so the condenser will continue to lose some additional heat, and it will be at a temperature, in this case as shown, if you measure it, to 115 degrees, and we have an additional 10 degrees of subcooling. Condenser split. That's the temperature difference between the condensing temperature and the air entering the condenser. So here we have our air entering the condenser, and we have our condensing temperature, which is the refrigerant PT relationship temperature. An example, we have 105 degree condensing temperature. We have a 75 degree entering air temperature, and therefore we have a 30 degree condenser split. Air-cooled condensers and condenser splits. A standard efficiency air conditioner and refrigeration condensers will have an air temperature coming in, and let's say around 95 degrees on that day. And we're going to have 125 degree condensing temperature. That's the refrigerant temperature. So the split's going to be 30 degrees. 95 from 125 degrees is a 30 degree split. On medium to high efficiency air conditioning condensers, you're going to find that we have 95 degree same ambient coming in at 95 degrees, but we're now going to, because of the design of the high efficiency or medium to high efficiency condensers, the condensing temperature of the refrigerant will be at 115 degrees, which will now give us a 20 degree split. So we could be looking anywhere from a 20 degree split for medium to high efficiency air conditioning to a 30 degree split for the standard efficiency air conditioner. Now the 125 degrees as shown there is at 278 pounds of pressure, and the 115 degrees is shown at 243 pounds. In other words, what you're seeing is the pressure-temperature relationship for saturation, the saturation pressure-temperature conditions. Notice on the medium to high efficiency air conditioning condensers, we have a lower pressure. That means that the compressor has less work to do to get to that higher pressure, and therefore it's going to consume less energy. Now, condenser splits do vary, and the manufacturer determines that split. But there are some common rules of thumb that you can follow. Most of the time, you're not going to have the condenser manufacturer's spec sheets. But on a standard refrigeration air conditioner, that's a 10 SEER, you're going to be looking normally at around 30 to 35 degrees. Somewhere between 30 to 35 degrees is going to be the standard SEER. Commercial freezers, we're looking at a condenser split of 20 to 25 degrees. That's a commercial freezers of 20 to 25 degrees. High efficiency air conditioners, SEERs of 13, 14, 15 and up, you're looking at 15 to 20 degree splits. If you have a remote refrigeration condenser, that means it is outside, up on a roof, out back in an equipment room, somewhere that is remote from, distant from where the evaporator is located, you're looking at a 10 degree split. Examples of condenser splits. Here we have a rooftop unit, air conditioner, a 30 degree split. Here's a freezer with a 25 degree split. Here's a high efficiency air conditioner, which is looking at a 20 degree split. And a remote, now this would be on the roof or sitting on the ground out back, remote from the evaporator would be a 10 degree split. So these are kind of rules of thumbs that you can go by when you don't know. Now, subcooling is equal to the condensing temperature minus the outlet temperature. That's the outlet temperature coming out of the condenser. The condensing temperature would be the pressure-temperature relationship from your PT chart. For example, on a standard system at a 95 degree ambient, we would have 125 degree condensing temperature minus a 115 degree liquid line temperature at the condenser outlet would give us a 10 degree subcooling. Now, where did the 125 degrees come from? Well, if it's a standard system, it's a 30 degree condenser temperature split. So we're looking at 95 plus 30 equals 125 degree condensing temperature. And then we check the temperature on the liquid line and we end up with 10 degree subcooling. Advantages of subcooling: prevents flash gas, or at least minimizes the amount of flash gas. For every 1 degree subcooling, there will be a gain of 0.5% increase in system efficiency. Here we see subcooling and the liquid line pressure drop, and this is going from nighttime to daytime. So let's take a look at this system. We have the conditions that are 90 degrees day, 120 degree condensing temperature, 90 plus 30 is 120 degrees. We have R22 at a 260 pound head pressure with our pressure temperature on our gauges. And in this particular case, we have a sight glass installed on this air conditioning system, which usually is not the norm, but let's say that we have installed one and we're going to see a clear sight glass. So we have a 90 degree day, we have a 120 degree condensing temperature, and the sight glass is clear. The pressure drop causes flashing. Let's take a look at that. The pressure drop in the vertical line, so we're running that refrigerant up the liquid line, vertically up to the attic where the evaporator is located. And we're going to find out that we have a 1/2 pound pressure drop per foot of rise. We can get that from charts and tables that will give us that information. Example, we have a 30-foot rise. It's a 3-story building. A 1/2 pound per foot gives a 15 pound pressure drop. So what we started out at the compressor condenser of 260 pounds at 120 degrees minus the 15 pounds is going to be at the metering device going into the evaporator, 245 pounds at the same temperature, because the 260 pounds is the PT relationship for saturation, and that's at 120 degrees. So we now have a lower pressure at the same temperature. The refrigerant 22 at 245 pounds boils off at 116 degrees. There'll be definite flashing at 120 degrees, because at 116 degrees and now we're at 120 degrees, there's a 4-degree increase there. Therefore, we will be getting flashing. So if we had the sight glass at that location, which is closer to the evaporator, we will see bubbles. That's not air in the system. That's the actual refrigerant vaporizing, going from a liquid to a vapor. Two things are going to happen. We're going to starve the metering device, which means that the evaporator will get less refrigerant. Therefore, there will be reduced cooling capacity. So flash gas does two things: starves the metering device, starves the evaporator, and reduces the cooling. So what we want to try to do is to either eliminate, or if not that, at least minimize the amount of flash gas that occurs. So let's take a look at what subcooling is here. Extra rows on the condenser equals subcooling. So we put additional coils, additional fins on the condenser, so that now the refrigerant has to go through the more of the coil and expose to more of the ambient, which will provide subcooling. So we're going to say that we get 5 degrees subcooling. So now we have 260 pounds of pressure liquid at 115 degrees. Now it's not coming out of the condenser anymore at the 120, it's coming out at 115 degrees because we have 5 degrees subcooling. We still have the same liquid line. The pressure drop at 15 pounds is 115 degrees. So the boiling point of 245 is 116, as we saw previously. So therefore, since we are at a temperature less than the boiling point, it won't boil. That means there is no flashing. So the sight glass at that remote location closer to the evaporator is going to be clear. So the advantage to subcooling in this case is to eliminate or minimize flashing. Now, ambient added heat to the liquid. Now let's watch what happens here. We have 245 pounds liquid at 115 degrees. We said that. We just saw it. No flashing. But attics are hot. For example, it could be 115 degrees, 150 degrees or more in that attic. And there you see the liquid line going across the attic a short distance, and that will be impacting that liquid line. Now, 115 degree liquid line in a 150 degree space, heat goes to cold, so the 150 degrees will want to get into where the 115 degrees is. So that means the liquid will get hotter. Now remember, we said at 245 pounds liquid boils at 116 degrees, but we find out now that we're going to get flashing in the liquid line because the liquid line will be getting warmer than 116 degrees. The factory designs from the factory is 10 to 15 degrees subcooling. Assume 10 degrees subcooling. Now remember, we worked on 5 degrees before. Now let's assume 10 degrees. Well, here we are back at the 120 degrees minus 10 degrees gives us a 110 degree liquid. There is definitely not going to be any flashing. 30-foot rise. Remember, the pressure at 240 pounds, 5 pounds is 110 degrees. No flashing because we're at or below the 110 degree flash point. We enter the attic at 150 degrees. The liquid line rises to 115 degrees. There is no flashing at this point. 245-pound flashes at 116 degrees. So as long as we stay below that 116 magic number, we're good to go. 1 degree from flashing is way too close to call, meaning the likelihood is that we're going to get some flashing at some point in time. 15 degrees subcooling would be safer. So if we have a system that is giving us 15 degrees subcooling instead of 10 degrees subcooling on that hot day in that hot attic, would be a lot better for the system to be able to get no flashing. And we see all 3 sight glass locations with no flashing. All right, moving on now to water-cooled condensers, we have what is known as a tube in a tube. The water flows in the inner tube. The refrigerant flows in the outer tube. So when there is a tube in a tube condenser, the inner tube has the water, the outer tube has the refrigerant. And the 2 surfaces reject heat. 2 types. Coil, 2 separate tubes, one inside the other, coiled up. That's why they call it a coil. Flanged, where there are 2 separate tubes in straight sections with removable flanges for cleaning. Here's a water-cooled condenser unit. There's a tube in a tube, but it's coiled. Water is coming in. The head pressure regulating valve, so we can regulate the head pressure based on the quantity of water coming in. For motor cooling, we have hot gas coming in and hot water coming out. So water in, water out. Cool water in, hotter water coming out. Tube within a tube coil condenser. Following is a picture of a cutaway view where the water uses the inner pipe and the refrigerant circulates around it. Here is one that has been cut apart, and the water is in, goes all around, and the refrigerant is going around the outer pipe. The inner pipe having water, the outer pipe between the 2 pipes is the refrigerant flow. There's the refrigerant coming in, hot gas coming in on the top there, and the liquid coming out. Notice the counterflow. Water, the cooler water is coming in where the refrigerant as liquid is coming out. The hot gas is coming in where the water is going out. So there is a counterflow. What you see here is no buildup in one tube on the inside of the tube where the water flows, where in fact there are mineral deposits shown in the upper left-hand corner. So this condenser eventually would become very inefficient at transferring heat. Now there's something called a shell and tube water-cooled condenser, and in this case the tank, which is the shell, is for the condenser liquid. The straight, which is the water tubes, go through the shell. The end caps are known as water boxes, which distribute water. So a shell and tube have end caps, and the end caps are commonly called water boxes. Note, the shell and tube water-cooled condensers are also called condenser receivers. So here we have a shell and tube water-cooled condenser sitting under the compressor here. Water is coming in and water is going out. The hot gas goes in and the liquid comes out. Here's what it looks like inside. The shell is a condenser and liquid receiver. So it becomes a condenser / liquid receiver. The tubes circulate water to condense the hot gas. So we have water flowing in the tubes and the shell has the refrigerant. Scale will also build up in these tubes from mineral deposits from the water. Cleaning rod is broken off in the tube. Now, in order to clean these tubes, you can actually take the water boxes off, which will expose these tubes, and you can put a cleaning rod down through them to clean them. But notice someone has broken a cleaning rod off in the tube and left it there. Here we see the shell and tube condenser with the water box with the cover removed, and you can see the tubes for the water flow. The end plate has been taken off. There are water circuits, and the water flows through there, in and out. Circuit has been provided for the water to flow in and out around through those tubes. And that ends this material on condensers.